Okay, hello. This is assignment 3, the solutions for it. So let's just jump right in. The first question, I was originally going to include a question about ray tracing, but because we did that activity in class and everybody participated and everybody got it, instead I just put a bonus question, and a few people did get it. It was Sally. If you were wondering where the answer was, there was one person at the college who does actually know the name, so a few people went and asked them and got the answer. But the other location where you could have found it was in the solution video to the very first assignment. I did mention her name once in that video because she interrupted while I was marking it. Okay. Oh, and that means everybody got 1 point because just at least one person got it. So, question number 2. What is the refractive index of a material if light passes through it at 2.3 times 8 meters per second? And we know that the speed of light is c, and I'm using an approximate value here of just 3 times 10 to the 8 meters per second. Our formula is just n equals c over v, where n is the refractive index, what we're looking for. So we get 3.0 times 10 to the 8 over 2.3 times 10 to the 8. And I'm going to move up over here. Now, if you go ahead and plug this into your calculators, you should get exactly 1.3. The 10 to the 8 on top and bottom actually just cancel out. So really you're just taking 3 and dividing it by 2.3. And you should get about 1.3 as your refractive index here. For question 3 here. Why must the core and cladding of fiber optic cables have different indexes of refraction? The hint here was to think about why one was larger than the other specifically. I was looking for a couple of things here. The main thing I was looking for was that they must be different to allow for total internal reflection. The index of refraction of the core must be larger. So core must be larger than the cladding. And this is because this will make light bend away from the normal. And when, this bending away from the normal means a larger angle of refraction. Let me just go ahead and shrink that. So when the angle of refraction is greater than or equal to 90 degrees away from the normal, then total internal reflection occurs. So I was looking for something along those lines there. Most of you ended up getting this done, but in far fewer words. I ended up giving you the full marks for that. But what I was looking for was how the light went through, and that was because of total internal refraction. And the only way that works is if you are going from a larger refractive index to a smaller refractive index, and the light bends away from the normal so much that it bends back into the first medium that it was traveling in. So that's why the refractive indexes have to be different, and why the core is the one that has to have a larger refractive index. Question 4 here. So in the diagram below, an incident light, that should say ray, not say. That is a typo. Light ray passes through air, then glass, then water, labeled on the left-hand side there for us. If the first angle of incidence is 13 degrees, I'll label that, what will be the final angle of refraction, theta 3? Now, this was a screenshot, not something I created, so there's some extra dashed lines from the original question here. Some of you, it looks like, took that as a hint as to how to take a little bit of a shortcut with this problem, where if you set it up just right, you don't actually have to do Snell's law twice. You can skip over the glass portion here. But anyway, I will show the long way, the longer way at least. So we are going to need Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. And so what we can set up here is something for theta 2, because what we are looking for is theta 2 currently. We know what all the refractive indexes are. We're looking for the final angle. So if I find theta 2 here, that is also equal to theta 2 down here. So if I use the given information on the first side, I will be able to find theta 2 down here. So if I set this up, the refractive index of air is 1, and the sine of 13 degrees equals refractive index of 1.52 and sine of theta 2, because that's what we're looking for. I'm going to divide both sides by 1.52, so that becomes the sine of 13 degrees over 1.52 equals the sine of theta 2. I'm going to write theta 2 on the left-hand side now. At the same time, I'm going to take the inverse sine of both sides. So I get inverse sine of the entire thing here. And plugging this in the calculator, I get 8.510700418 degrees. The reason I'm keeping so many digits is because I know that this is not my final answer, and I want to keep at least a little bit of precision. So now I will be setting up for the second half. So I know that this theta 2 is also this angle right here. So now I'm going to set up the second Snell's law, which starts in glass. So my n1 is 1.52 sine of the long decimal. And we are moving into water, so I use the refractive index of water for theta 3 side, for the right-hand side. So same thing, I'm going to move the 4/3 to the other side. Now, two ways you could write it, really. You could write it as the whole left-hand side being divided by 4/3. Or you could multiply everything by 3. So you could write it as 4 over 3, like this. But what I think is a little bit easier is multiplying everything by 3 to cancel out the 3 on the bottom of that fraction, and dividing everything by 4 to cancel out the 4 on the top of that fraction. So you end up just getting 3 over 4 in front. So 3 over 4 times 1.52 times the sine of that angle is all equal to the sine of theta 3. Now, again, I'm going to write theta 3 on the left, and I'm going to take the inverse sine of both sides at once here, and I will have 3 over 4 times 1.52 times the sine of our long decimal here, careful with your brackets on this one. I tried doing it all in one step. My calculator gave me a syntax error. Not sure exactly what I did. I broke it down into smaller steps. My calculator spat out an answer, no problem. So really easy to make mistakes there, putting everything in one line. But if you do it properly, it will work. Just careful. And this gave me 9.7 degrees as my final answer here. So that was number 4. The shortcut that I briefly mentioned, I will write in, let's go blue here. The shortcut was basically to go, instead of from air to glass to water, to just go instead straight from air to water. This works because you have n1 sine theta 1 is equal to n2 sine theta 2. But then we also say that n2 sine theta 2 is equal to n3 sine theta 3. So what we can actually say is n1 sine theta 1 is equal to n3 sine theta 3. So if done properly, you can skip the glass portion entirely. Don't need to calculate theta 2. Don't need to use n2 equals 1.52. Again, if done properly. Some people tried this, and some people worked, some people didn't, but it does give you the right answer. Give it a try. So, question 5. A light ray travels from water to a mystery substance. The angle of incidence is 10 degrees, and the angle of refraction is 14.9 degrees. The index of refraction of water is 4 over 3. And I ask you for the index of refraction of the mystery substance. So again, this is a Snell's law question. So we're going to start with the index of refraction of water times the sine of our angle of incidence of 10 degrees. And the index of refraction, here's what we're looking for. So I will leave that as n times sine of 14.9 degrees. I'm going to rewrite this so what I'm looking for is by itself on the left. And I'm going to divide everything by the sine of 14.9 degrees. So I'm going to have 4 over 3 sine of 10 degrees all over top of the sine 14.9 degrees. And calculating this out, I get an n of about 0.9. So that was the correct calculation there. And in B, I tell you that something is unreasonable about part A. What I'm looking for here is basically you to just tell me that the unreasonable part is that it is less than 1. This implies that light travels faster in this mystery substance than in a vacuum. And with our current knowledge and technology as humans, we believe this to be impossible. So that is what is unreasonable about 5A. 6, down here, there are 4 mistakes in this that I did on purpose. I asked you to correct them. So first I'm going to go ahead and label these light rays so we know what I'm talking about. Light rays 1, 2, and that was supposed to be a 3. Light rays 1, 2, and 3. So first I will talk about light ray number 1. This light ray should have refracted when it hit the lens. So refraction should have happened. Should have happened. And this refraction should have gone straight through the focal point, like this. Number 2, light ray number 2, I have drawn this as theta 1 and theta 2 being equal to each other here as well, with that little equation down at the bottom. And this is bouncing off the optical axis as if the optical axis were a mirror. However, it's not. The optical axis is just something we draw in. It has no real physical analog in a real experiment. The only physical portion to this is the object and the converging lens that we have here. Also, I should mention that I know that the refracted ray of number 1 goes down through the focal point because this is a converging lens. I know that because of the arrows on the blue lens pointing outwards. That indicates a converging lens. So light ray number 2, a ray that goes through the center of the lens should keep going through unrefracted. So that's almost parallel. Good enough for my sketch. That's what should happen. So it should continue to pass through. Should continue without refracting. In this case, it is because it's going through the center. And number 3 here, it's going from the bottom of the object to the top. So it goes from bottom to top of object. That is what's wrong with there. And you could have said one of 2 other things. I guess technically there's 5 mistakes. You could have drawn in a new image over here and said that this was the 4th mistake. So proper image location. Or you could look at light ray number 2 and see that theta 1 and theta 2 are actually measured improperly. So if we consider where the lens is to be our normal for theta 1, theta 2, this is how we should measure them. We measure from the normal, not from the horizontal. So in this case, theta 1 does not equal theta 2. Almost like a bit of a bonus mistake. Not measured properly. So I did put 5 in there just to up your chances of seeing extras, I guess. But the intended 4 were the first 3 I did, plus the 2 angles being different. Some people considered the image not being in the right place a mistake. I considered that like a extra mistake, I guess, as well. So I gave you the mark if you pointed out that one, because I was not explicit. So totally worked. You were correct. Moving on, number 7. Now this one I did not count because I was very unclear about this one in class. It is possible, but the index of refraction must be less than glass. And I don't explicitly say it's glass, but I did imply it was. So this will work for something like an index of refraction of 1.4-ish. So if we take a look at what I already had over here. Geometric optics on PHET. Let's switch this down to there. Perfect. Now this is just like our setup. And you can see that our image on the left, the tall one, can be created by an object by a converging lens within the focal point. So if I head back, we know that there should be a light ray going from the top of the object through the center of the lens. So I know that there is a light ray going along this line for sure. I also know that an object or a light ray coming off the object will go through the lens parallel to the optical axis. So I know it will go through the optical axis parallel, which means that I can trace it back to the object parallel as well. And what will have created that object, or that parallel light ray, a light ray that refracts parallel, is one that goes or comes from the direction of the focal point like this. Just like so. And already I have enough information to find where my object is, which would be right there, drawn in red. So this here would be the object, just like that. Now, if we go back, you can play around with the distances here, and you can see just how the light rays move around. Why don't we finish this off by drawing the last ray? Now, this last one's a little bit more complicated because you need a second focal point at about 6.5 centimeters, or 6.25 centimeters away. So we have a second focal point around here somewhere. And we know that a light ray from the object leaves parallel will refract through the far focal point. So if I draw this line here going through the focal point, I know that it was created by a light ray that came out, or came to the lens parallel. And I can trace it back to find my object. And you can see that they all intersect. So it is indeed possible, because of the uncertainty and confusion surrounding this question in class, I ended up taking it off. If you were curious of the solution, this is the intended solution to this problem. So this was the last of assignment 3. Again, if you have questions, please just let me know in class or email me. Thank you.